All right, now I'm going to talk a bit about spatial sampling. So how do we collect and gather spatial data? And then I'll loop back around to talking a little bit about how we can exploit a little bit of the special nature of spatial data. You can think of sampling as the process of selecting points from within an area. This area is also sometimes referred to as the sample frame. We select some areas from within the frame, but we discard others, right? So as I've talked about a bit already, the world is essentially infinitely complex. There's no way that we can capture and describe everything about it all at once. So depending on the task at hand, maybe we focus on just one subset and collect all the information we can about it, or maybe the reality or the area that we're looking at is too complex and we have to just stick to looking at a subset. So we take samples of that area and use that to work with. But how do we choose which points we can keep and determine the quality of our data? Scientific sampling requires that each element in a sample frame has some pre-specified chance of selection. If some elements have either a greater or lower chance of being selected, then our sample is said to be biased. And if every element of interest has an equal chance of being selected, then our sample is said to be unbiased. Now, biased isn't necessarily a bad thing in the context of spatial sampling. Sometimes we explicitly design our samples to be biased. Even though, again, in many of the hard sciences, you want an unbiased sample. Sometimes that's just not a feasible option in geography. Because again, objects that are close to each other are more likely to be related. Things that are farther away are more likely to be less related. In theory, a completely random, that is unbiased sampling process is best. With this, each location has an equal chance of being selected. One of the advantages of a random sample is that it's fairly easy to do, at least in theory. I'll explain why it's not always easy in practice, but it's easy to define. You create your sample frame, that's the area that you're looking at, and then you just randomly generate X and Y coordinates within the sample frame. Typically speaking, this provides a good range of possible values in a distribution. However, sorry, the dog is chewing on a squeaky toy. However, there is a chance that all samples will be taken from the same type of elements within a certain population. So for instance, we might only sample from urban areas and misforested areas, and it's often difficult to implement this in practice. So if you look at the figure down here, you can see some of the drawbacks of random sampling. So all the blue circles are the samples we take. And with random samples, you might end up by chance oversampling large elements like a building or a crop field. So these are homogeneous areas where you don't need a lot of samples to describe what they are. Or you might completely miss smaller elements. So for instance, maybe there's some certain tree species in an area that you need to get samples from. If you rely on a random sample, maybe you'll miss all of those trees, and then you won't include that in your abstraction of reality. We have a number of approaches to limit the impact of this. We can do repeated sampling. So theoretically, if you repeat a random sample over and over and over again, you'll get a lot more samples and it'll be more representative of the entire population. The downside to this is that it's more time consuming and it requires more resources. Typically speaking, collecting data physically, going out and doing it, is fairly expensive. You have to pay people to collect the data or invest your own time in it. It's labor intensive. It's a lot of work. If you've ever done any field work, you know that it's a lot. So typically we don't want to do just random samples. You can end up with a lot of redundancy of labor and things like that. Generally speaking, in geography, we rely on biased systematic sampling methods instead. So this is where we create some sort of sampling design that trades a sampling scheme for randomness. So instead of complete randomness, we define some structure. We induce some bias to our sample. But we do that with the intent of making our sample easier, more spatially representative, things like that. So systematic sampling isn't perfect either. It may miss some features that have a regular pattern or cluster, but we can make some adjustments to that to compensate. A systematic sample is just where some sort of regular grid is imposed on the sample space to ensure evenness. So this can be a solid strategy for areas that contain only a handful of features with abrupt boundaries like buildings or something. But it's not ideal for things that exhibit some degree of periodicity, that is like regular intervals, like roads, because you might end up oversampling or undersampling the feature if all of your sample points match up with the period of whatever entity you're looking at. So for instance, if you overlay a grid on a road network, it's possible that all of the sample points might completely miss the road network. It's also possible that the samples might mostly fall on the roads. So the purely systematic sample, generally speaking, isn't the best option here. One workaround is you can combine the benefits of the systematic sample with the benefits of a random sample. Generally speaking, the systematic sample is nice because it makes your sampling scheme a bit more organized and regular. It's usually easier to collect, but you get rid of all the randomness. Instead, you can address this issue by defining a regularly spaced grid and then taking random samples within them. So this induces some randomness to the sampling method and will alleviate issues with overlapping periodic features. However, this goes back to the main issue with one of the main issues with random sampling is that it's time-consuming and costly. Alternatively, another form of stratified random sampling is you can rely on the grid method as in figure D on the bottom left, but you can space the grids at random intervals instead. It's essentially doing the same thing. Another option is cluster sampling. So you can do intense sampling of features in clusters around a number of selected locations. This is useful if you know that you want to focus on certain areas. So for instance, shopping centers. Maybe you want to do a survey of the opinions of shoppers for some certain thing, right? It might make sense to send canvassers to specific shopping centers to interview people who pass by. It wouldn't make sense to send one of your canvassers to a city park to ask them their opinion on something if it relates to shopping. It wouldn't be a good idea to have the surveyors go door to door, right? You're not necessarily going to be getting the target population you're looking for. That would be a waste of resources to go to a park or to canvass a neighborhood when they could simply stand outside of the shopping center and get the target population they're looking for. So that's one context where cluster sampling is very beneficial. If you are working with things that are specifically clustered and you know you just want to target those things, you can ignore the rest of the sampling area. Another option is to just randomly define or you can select the cluster locations at random and then intensively sample those clusters. So this could be beneficial if you're trying to do a vegetation survey, for instance. You have a large area and you randomly define vegetation plots, and then you take samples within those vegetation plots. So again, this allows you to use some of the randomness and exploit some of the advantages of unbiased sampling, while also exploiting some of the time-saving advantages of biased sampling. So you choose a handful of random locations and then intensively sample them, rather than sporadically sampling a whole bunch of random locations. This is really efficient time-wise, but it might not be representative of the broader population that you're interested in. Another option is transect sampling. So this allows you to focus your efforts only on a specific area of interest. It's a really efficient way to sample just the key feature that you're looking at. You don't sample outside of the focus area, but one drawback is that it requires really good pre-existing understanding of the spatial structure of the object or whatever you're studying for maximum effectiveness. The most common application for this type of sampling method might be along linear features like roads or rivers. So you want to get a stream profile. You just define transects across the stream, and so you just focus on those specific areas. You don't need to focus outside of the stream. And also, because of the sort of effort and difficulty involved with like measuring stream depth, you have to have somebody walk across that stream. It might be easier to just have them walk in lines across the river rather than trying to navigate it and doing random samples at a bunch of different locations. And then within the transect sample, samples can either be randomly spaced, stratified, or some combination of the two approaches. So with most of these different types of sampling methods, you can induce some degree of randomness to make them a little bit less biased if you want. How many samples do we need? The number of samples required to adequately represent a population is a function of how similar the units of a population are. So if you think about the spatially homogeneous tree farm example, if we have a field where all of the trees are the same species and they were planted in the same year, they're all given the same amount of fertilizer, grown under the same light conditions, there's going to be some small degree of variability in tree height. So you want to measure the average height of the trees across this field. You might need to sample, say, 30 trees and go around and measure their height. You can take the average and get a good idea of the average tree height on this tree farm because it's fairly homogeneous. They're all essentially the same. Whereas if you want to measure the average tree height in a natural landscape with a high degree of spatial heterogeneity, you're going to need more samples. You've got different tree species. The trees all sprout in different years, especially if it's like an old growth forest. You've got different soil conditions, a variety of factors that are going to lead to trees of different heights spread across the landscape. So you're going to need a lot more samples to determine the average tree height in this landscape than this landscape. And due to spatial heterogeneity, because structure can vary widely across the landscape, it's important to have a bit of knowledge about your study area. This is going to help you determine what the best sampling method is, because the goal is to maximize returns for minimal effort. You need to balance effective coverage with the cost of collecting the data. And I mean cost not just in money, but in time and in effort. So, as is often going to be the case in this course, there's no one right answer. The specific type of sampling method that you're going to use will oftentimes depend on the features that you're looking at and the resources you have to conduct whatever analysis you're working on. So now I'm going to briefly take a moment to talk about one of the techniques that we can use to exploit the special nature of spatial data. What if we have a data set where we took some samples, but we want to know what falls between the samples? We can do something called spatial interpolation to figure out what might go. So this is a really simple one-dimensional example. So you've got a string of numbers, 1, 2, 4, and 5. We didn't sample the middle one. We want to know what's there. I think we can all assume that it's going to be a 3. If you take that to 2 dimensions, things get a little bit more complicated. But again, you can fill in the blanks using the patterns observed in the data set. So this is known as spatial interpolation. And the process of filling in blanks in general is known as interpolation. So if you do it over one dimension, 1, 2, 3, 4, 5, that's known as linear interpolation. But if you do it over 2 or 3 dimensions, then we're going to call it spatial interpolation. Essentially, it's just intelligent guesswork where we attempt to make a reasonable estimate of values of a continuous field at a place where we don't have measurements. Spatial interpolation only makes sense for a continuous field, so something where it varies across space, like temperature or precipitation or elevation. With categorical data, like land cover, it can be a pretty problematic thing to do, and it doesn't work very well. So spatial interpolation works really well with rainfall, temperature, pressure, most weather observations in general. So you can use it to make estimations between weather stations. So Canada has a network of weather stations spread across the country, some more dense in populated areas, some more sparse, especially in the north. But we can use the information from these weather stations to estimate the average temperature at all spaces, at all locations across the country by interpolating between the values at weather stations. It can be used to measure or estimate elevation between measured locations, and it's also used when we change resolution of raster images. So all spatial interpolation methods incorporate distance to known samples, and if this sounds familiar, that's because they exploit Tobler's first law of geography. Closer samples are going to be given more weight than distant ones. And a threshold is usually set to determine the maximum distance to take samples from. Most continuous fields tend to exhibit very strong spatial autocorrelation, so it's pretty reasonable to assume that values that are missing are likely to be similar to those that are around them in the field. So here's just a visual example of how you might go about doing spatial interpolation with elevation data. There's a tool called inverse distance weighting where values are interpolated based on their distance from known points, where the farther away the object is, the less weight it has. That is, it is inversely weighted with its distance. So you can see a one-dimensional and two-dimensional example of inverse distance weighting, where on the left, using it to just interpolate the values between points on a line, and on the right, we're using it to estimate elevation across space given a small number of samples. So I will discuss, or I'll show an example later on in the term of specifically how to do inverse distance weighting in ArcGIS Pro, but I just wanted to introduce this concept because it kind of ties in nicely with what I've already talked about.